So we're talking about numerically summarizing data. Chapter 2 is all about how to represent it in a graph or in a chart, how to visually represent our data. So now we're going to use numbers to summarize what we have. A lot of this, again, you've already seen, but we're going to change the notation a little bit. We're going to change the way it's represented. So when we look at the arithmetic mean of a variable, you already know what this is. It's just the mean. We're going to add all the values together and divide by the total number of observations. So just like if you were going to average together your test scores, you would add all your test scores together. And if you had taken 5 tests, you would divide by 5, and that would give you your average test score. When we represent the population mean, we use that Greek letter mu, that funny looking U. Now remember, a population summary is called a parameter. If we want to use it for the sample, it's called a statistic. So for the sample mean, we use this X bar. So the X with the line over it is what represents it. So the difference, we've got the population mean, which is represented by mu. That's if we know everybody in the whole class's test grades. And then we've got the sample mean, which is represented by X bar. So if I randomly picked 5 people out of a hat and averaged their test grades together, that would be our sample mean. So we know what the formula looks like. We could write it down as test 1 plus test 2 plus test 3 plus test 4, and however many tests we have divided by that total number. That other notation on this slide, that sigma x, just means the sum of all the x values. It's kind of a shortcut way to write the formula for that arithmetic mean. So just a fancy way to write the sum of all of those pieces. Again, it works for a sample. The difference here is that instead of using a capital N, that means the total number, we're using a lowercase n, which is just the sample size. But same approach, same process. Now I'm going to show you all of the equations to calculate each one of these summary statistics or parameters, but your calculator and StatCrunch and any kind of spreadsheet that you use, we should be able to get those summary statistics and parameters from those programs also. So it's not that we use the formulas that often, but you have to know where the numbers come from. So this is just an example, and again, I'll post this so that you can read through it, work through it, and make sure that you get the same thing that's presented in the examples. But for this particular problem, they're saying, here's the information for 7 different employees, and we want to take a simple random sample of 3 of those. So a couple of ways that we could do it, we could do put them in order from least to greatest and do a random number generator and say, well, I'm going to pick the first one, the third one, and the 4th one, or whatever those random numbers are, and just find the mean for those 3 values. We could put them in a hat and draw out 3. Lots of different ways that we could get a sample of 3 out of this set. So this is the population mean, adding all of those values together. So the population mean is 24.9 minutes. So we've added up all of those outcomes, divided by 7, because that's how many pieces of information that I had, and we got that 24.9. We would also be able to do a sample of 3, and hopefully we would get an outcome that was similar. It's not going to be exactly the same, but hopefully it would be similar. So our next measurement these are measures of central tendency. So I'm trying to come up with what the center of my data looks like. So the mean is one measure of central tendency. The median is another measure of central tendency. So the median, just like you learned before, is the middle. So if we put our data in order from least to greatest and I count in from the middle, if it's an odd number of values, it'll be that middle term. If we have an even number of values, then we'll have to average together those two middle terms. So here are our steps, exactly what you've done before. Put it in order from least to greatest or in ascending order. And then figure out which piece of information is in the middle of that list. Now, we can get pretty fancy and say that if we have an odd number of data, then we can do, let's say we had 9 pieces of data. 9 plus 1 is 10. 10 divided by 2 is 5. So if I count in from either side, it's going to be the 5th term. That 5th term is going to be the very middle term of those 9 pieces of data. Now, you could put it in a list and mark off the top and the bottom until you got to that very middle term, which would give you exactly the same thing. If you don't have a lot of data, it's not a big deal to mark it off from each side and circle that middle piece of data. But if you had a lot of information, it might be easier to take this approach. Again, this is just a fancy way to do it. You can put it in your calculator, you can put it in any kind of spreadsheet, and you should be able to find the median of any set of data as long as you have all of that data typed into that spreadsheet. So this is just putting what our process is into mathematical terms. Same thing as count in from both sides. So here's an example, that same information about travel times to work, and we've put this information in order from least to greatest. I know that there are 7 pieces of information. So if I have it in order 5, 18, 23, 23, 26, 36, 43, and I mark off from both ends until I get to the center, I know that the middle term is going to be that 23. If we wanted to, we could say that it was the 4th from each side. So 5, 18, 23, 23 is the 4th term. If we counted from the other direction, 43, 36, 26, 23 is the 4th term. So just get into the middle. So let's say instead we've got 8 pieces of data. So in this case, we've added another employee, and now we have their piece of information too. If we want to find the median, just remember that we have to take those 2 middle terms and average them together. So over here we had a median of 23. If we add another person in, we're looking at the median of 8 terms, so we have to average together 23 and 26 because those are the 2 in the middle when we put them in order from least to greatest. So that means it's going to be 24.5 now instead of 23. So our median has gone up just a little bit based on that new piece of data that we've added in. If the median and the mean both give us a measurement for the middle of my piece of data or my set of data, they give us that central tendency, a measure for the middle of my data. How do we decide which one we're going to use for a certain set of information? Do we just always use the mean because that seems to be more reliable, or should we change to the median sometimes? Well, this is going to kind of help us out with that. Suppose we have a new employee that's been hired and we're going to add their data in to that set that we have of 7 pieces of information. So our new person has a 130-minute commute. Now, based on what we had already, we had commutes anywhere from 5 minutes to 43 minutes. That was the extent of it. So everybody was pretty close together, but now I have this person that's driving from far away. They've got a 130-minute commute. So should I use the mean or the median? We'll look at the mean before we hired somebody new. The mean was 24.9 minutes. If we add in that 130-minute commute, my mean is now 38 minutes. Look how far that jumped up based on that one piece of data. If we look at the median before and after, the median before we added that new person in was 23 minutes. The median after was 24.5 minutes. So what we say is that the median is resistant. It's resistant to outliers. So if we have something in there, let's say we're looking at test grades, and one day you were absent and you didn't make the test up and you ended up with a 0, but all of your other test grades are like B's. Well, I'm going to take the average, and that 0 is really going to pull your test grade down or your average down. So based on that, you would prefer that I take the median grade, because the median grade is not going to be nearly as affected. It's still going to be a B if all of your other grades are B's, even after you add in that 0. So the median is resistant. The mean is affected by those outlier values, those values that don't fit into the norm. So there's that summary. A numerical summary of data is said to be resistant if extreme values, either really big or really little, that don't fit into the rest of your pattern, do not affect the value substantially. So there's not a big impact on your summary statistic based on those extreme values. So let's look at what that does to a curve. If our information is symmetric, if we look at that middle graph, the mean and the median should be the same. So everything is equally dispersed. If we find the mean of that value and the median of that set of data, then they should match up pretty well. They might not be exactly the same, but they're going to be really close. Now, if we have information that's skewed to the left, look at graph A. If we have information that's skewed to the left, that means that my mean is being affected by all of those much smaller values to the left. So notice how the mean is smaller than the median. The median's closer to the top of that hill. And on the other side, if we look at graph C, that one's skewed to the right. We've got some values that are bigger that don't fit into that pattern. So the median is closer to the top of that hill, and the mean has been pulled in the direction of all of those larger values. So the mean is greater than the median. The mean is always in the direction of that tail because it is not resistant. So if I had a set of data and I gave you the mean and the median, you should be able to tell me what the shape of that distribution is. So this is just a set of data. It's the prices of homes that are for sale in Lincoln, Nebraska. If we were to find the mean and the median, we see that the mean is $168,320, but the median is $148,700. So go ahead and calculating the mean and the median for you of this whole set of information, that's what we have. So based on that, knowing that the median is smaller than the mean, we would make the prediction that if we were looking at the histogram of that data, or if we were looking at the curve of this data, it would be skewed to the right. Okay, so if we were looking at that histogram, then it would be skewed to the right. We would have most of our values that fall within a certain range, and then it would tail off to the right. We would have some outliers maybe, or some that don't fit into the pattern that are more expensive than the other houses. So that's what that histogram would look like. Okay, so continuing on with measures of central tendency, another measure of central tendency, so another way that we can look at the middle of the data, is to look at the mode. So just like you've looked at mode before, it's the one that occurs most often. So mode, most. Um, and it's okay if a data set doesn't have a mode or if it has more than one mode. So for this one, we've actually got a set of information that is qualitative, it's categorical. These are the vice presidents in the state that they were born in. So if you just look at it represented this way, but if we create a frequency table, just scanning down the numbers and the frequencies or even looking at that tally, it's pretty easy to see that one state jumps out, and that's New York. So obviously, New York would be the mode for those two sets of data. So the three things that we've talked about so far as measures of central tendency go, we've talked about mean, median, and mode. So things that you've had experience with before. The only thing we've done is added some more technical ways that we can represent this. We've changed the notation a little bit. So next we want to talk about dispersion, or the way the data is spread out. So we've talked about the center. Now we want to talk about the spread, or the dispersion of the data. So we're going to use this example to walk through the way the data is spread out and the shape of the data overall. We're going to be ordering food from McDonald's or from Wendy's. Now for McDonald's, you've got multiple lines that you can choose from. For Wendy's, we've got just a single line and we're going to move people through that line. So the following data represents our wait time in minutes. And we've got 30 customers for each one during lunch hour. So how long people have to wait whenever it's busy. So we want to find the mean and we want to draw a histogram. These are our two sets of information. Now we could put these in the calculator, or we could put these into a spreadsheet and we can find the information. If you're putting it into your calculator, if you have your Casio and you go to menu and that second option, which is statistics, you can enter a list of data. Now, if you want to find out what the mean, median, mode, standard deviation, all of those things that we're getting ready to talk about, if you want those calculated in your calculator, you go to option 2, which is statistics, enter all of your information into that first list, and then press F2, which is calc, and then F1, which is representing that one variable set of information. So if you press that, then you should get all of this information given to you. Now, everything's going to be based on the information that you enter. So if it's a population, you want to make sure you pay attention to the population statistics or parameters. And if it's a sample, then you want to look at those sample statistics. So mean wait time in each line is 1.39 minutes. So based on that whole set of information, the mean in each one is the same, 1.39. But if we create a histogram for these two sets of information, the histograms look a lot different. So look at those two quickly and see what's the same or what's different, how they vary. So looking at the Wendy's, that looks like it's more bunched up together. It's obvious that most of my wait times are between a half a minute and 2 minutes. And we've got a couple of other values that fall outside of that range, but most of them fall within those values. If you look at the McDonald's wait time, it's a lot more spread out. So I could share my opinion and say, well, it looks like it's more spread out. Or I could come up with an actual numerical value to share to prove that it's more spread out. So that's what we want to have, is something that's more concrete than just an observation of a graph. Observations of graphs are great. But we need some values. We need to know how spread out it is. So one measure of dispersion is range. So just like you've looked at before, the biggest number minus the smallest number gives you the range of a set of data. The next measure of dispersion that we're going to look at is standard deviation. So standard deviation helps us know how spread out my data is from the mean. And if we want to represent the population standard deviation, it's going to be represented by a lowercase sigma. And if you calculate these values in your calculator, it's represented as sigma with an X beside it. So that's the one that you would be looking at if you use your calculator to find that value. This is what the formula looks like. Again, this is dependent on how many pieces of data you have. It's the piece of data minus the mean of the population squared. And you add that value together for all of the outcomes, all of the pieces of data that you have, divide it by the total number of pieces of data, and then take the square root. It's ridiculous to do if you have a large set of data. So I would suggest using your calculator or a spreadsheet program to find this. It's good to know where the formula comes from, but honestly, it's not something that you're going to sit down and work out. So this is for population. That's what it looks like. If you use the computational formula, again, I would type this into my calculator. I would not plug it into a formula. The only thing that changes when we're looking at information from a sample as opposed to the population is that instead of dividing by the total number of pieces of data, we're going to divide by n minus 1 pieces of data. So it's just going to change a little bit. Now, n minus 1 is called degrees of freedom. I'm pretty sure it comes up on the slide in just a second. But it just controls for the fact that we're dealing with a sample and not the whole population. When we look at this represented, it's represented by an S for sample standard deviation, and in your calculator, it's represented by SX. And there's our information about degrees of freedom. So just making sure when we use a sample, it's n minus 1. So going back to that data about Wendy's and McDonald's, we've looked at where the middle is. We've looked at what the graph looks like. Now, if we find sample standard deviations from Wendy's and McDonald's, remember we just took a sample of that lunch hour and we're comparing those two. Notice, remember Wendy's looked like it was grouped closer together and McDonald's looked like it was spread further apart. So the Wendy's standard deviation is smaller, 0.738 minutes, than the McDonald's sample standard deviation, 1.265 minutes. Something else that's looked at when we look at dispersion is the variance. Now, honestly, variance isn't used quite as often. It has been traditionally a stepping stone to get to standard deviation because in order to get from variance to standard deviation, you take the square root. So it was kind of a stepping stone. It was a way to get from this is the value that I got for variance. If you take the square root of it, you get the standard deviation. So that's something that we're able to find, but it's less applicable. We don't have information that's given to us in the same units that our original problem was. If you have experience with any kind of statistics or normal distribution, you probably know about the empirical rule. So when we're looking at that bell-shaped, normal, symmetric curve, our mean and our median are lined up in the middle at the tallest point of that curve, and then everything on both sides are very symmetric. So within one standard deviation of the mean, we have about 60%, 68% of the information of the data. So that's kind of your normal range. If you score within one standard deviation of the mean, you're pretty normal as far as your test score or whatever goes. If you move on out to 2 standard deviations away from the mean, you're at 95% of the data, and then 3 standard deviations away is 99.7. So most of your data, if you're dealing with the normal curve, is going to be within 3 standard deviations of the mean. You can use this for a population or for a sample. But this is what it looks like, and this is a really good representation. It breaks it down not only into within the standard deviations, those big portions at the top, but also into each little piece um, of your curve. It's broken down into those portions also. So notice that your mean is in the middle. It's the tallest point. And if we were to find the median, it would fall in that same place because it's symmetric. So if these were like SAT or ACT scores, and you're looking at your percentile score, so you scored as well or better than whatever percentage of the people who took that test for that time frame, we would be looking at a normal curve. So if you knew your standard deviation, again, if you're within one standard deviation of the mean, that's pretty average. That's where most people are. 68% of people who took the test fall within one standard deviation of the mean. Now, if your test score translated to a z-score or a standard deviation that was 2 standard deviations above the mean, then you're doing pretty well. There aren't a lot of people that scored better than you on the test. So just looking at the comparisons above and below the mean on that graph.